Now dear students of class 12, we are coming to Coleridge's law of independent migration of ions. Now Coleridge studied a lot in infinite dilution the molar conductivity at infinite dilution of strong electrolytes with common anion here. Common anion Cl is here, but cation is different, and their molar conductivity at infinite dilution measured and get the difference of for NaCl or NaCl get the difference 23.4 Simon centimeter square mole inverse. Just keeping the cation same, change the anion and find out the molar conductivity at infinite dilution, and he found that the difference is still 23.4 Simon centimeter square mole inverse. That means the molar conductivity at infinite dilution of these cations for K plus and Na plus is independent and irrespective of the anion present. Their conductivity of cation of K plus and Na plus is being same at infinite dilution, irrespective of whatever the anion present here. So in case of anion also, with the common cation, the anion also he got the same result, that the anion also conduct the at infinite dilution conduct or contribute a certain amount, definite amount to the conductance, molar conductivity. That means he come to a law which is known as Coleridge's law of independent migration of ions, that at infinite dilution each ions makes a definite contribution towards molar conductivity of the electrolyte, irrespective of the nature of the other ion with which it associated. That means whatever the other ion associated, it does not depend on its own conductivity, and this conductivity is called, each ion conductivity is called molar ionic conductivity, molar ionic conductivity, and represented by lambda. Now thus at infinite dilution the molar conductivity become V plus, this is the valency, this is the number of cations coming per formula, and this is the molar ionic conductance, and this is V minus means number of anions coming from the formula, and this is the molar conductance at infinite dilution, molar conductance of ion at infinite dilution. Now that's for example for MgCl2, how many Mg coming from the formula? 1 and 2 Cl minus ion coming. So it will be the molar conductance of Mg plus ion into 1 plus 2 into molar conductance of Cl minus ion, molar ionic conductance of Cl minus ion. So we can write as a contribution of the each ion, and the contribution is will be same in the case of molar conductivity, whatever irrespective of the anion or the cation present. That means Mg plus ion, whatever it carry electricity, it carry electricity at infinite dilution. If Cl minus ion not present, if other ion Br minus ion present, then also the value will be, magnitude will be same. Now how we apply this Coleridge's law? Now the application of Coleridge's law is first that calculation of molar conductivity at infinite dilution for weak electrolyte. Now weak electrolyte we cannot find out the molar conductivity at infinite dilution from the graph. So we take the help of Kohlraasch's law and we can calculate. Suppose you have to calculate the molar conductivity of acetic acid at infinite dilution, and acetic acid means it will be the acetate ion and molar conductance plus H plus ion molar conductance. Now we are taking three strong electrolyte. One is sodium acetate. It's split into this way, giving this ion conductance, and HCl giving this ion conductance, and NaCl giving this ion conductance. Now we can find out the value of this strong electrolyte at infinite dilution from the graph. So we can easily find out the values for these three strong electrolyte. Now if we subtract, first add this sodium acetate, molar conductance of sodium acetate at infinite dilution with molar conductance of HCl at infinite dilution, and then subtract it from the molar conductance of NaCl, we get the ion conductance of CH3CO minus and H plus ion. So that means we get the molar conductance of CH3COH at infinite dilution, not by the direct way but the indirect way of using Kohlraasch's law. Second is calculation of degree of dissociation. Degree of dissociation can be calculated by degree of dissociation alpha equals to molar conductance at any concentration by molar conductance at infinite dilution. And we can also calculate the dissociation constant. We know that dissociation constant means K equals to C into alpha square, that is degree of dissociation, divided by 1 minus alpha. Now if I put the value of alpha here in this equation, we get C into, that is concentration, into a molar conductance square at that concentration, divided by molar conductance at infinite dilution into molar conductance at infinite dilution minus 1. So in this way we can calculate the dissociation constant, and also we can calculate the solubility of sparingly soluble salt like barium sulfate or silver chloride. Now barium sulfate or silver chloride is sparingly soluble, so their concentration at anywhere in this aqueous solution is almost infinitely diluted. So their solubility we can calculate. Solubility equals to small kappa into 1000 by molar conductivity of that salt at infinite dilution. So this is the application of Kohlraasch's law, and this is the application of Kohlraasch's law. There are 4 applications are there. So I think you can go through this, and in mid class I could ask you and give you some assignment.